Okay, I'd like to welcome everybody to this third keynote session of the conference, and it's my pleasure to introduce Saeid Nahavandi. He is distinguished professor of Swinburne University of Technology in Australia, and he's a long time active in the society. So his research focus is mainly on intelligent systems and intelligent control in more general. So he's working since many, many years in this field. And his main research interests include modeling of complex system, robotics, and haptics. A bit of his CV, so just to point out some of his major steps, Said received a PhD from Durham University, UK in 1991. He is currently Associate Deputy Vice Chancellor Research and Chief of Defense Innovation. He was Funding Director of the Institute for Intelligent Systems Research and Innovation, Australia. He has, for those of you who are interested in this famous H-index numbers, he has over 1,300 scientific papers, and his Google Scholar citation count is above 37,000 citations, and the H-index is 92 currently. So he's quite well perceived in the community. From the perspective of SMC, he is currently Human Machine Systems Vice President, and interestingly, he has received a lot of awards, and among it, the Clooney Ross Entrepreneur of the Year Award. So he's not only doing research in theory, he also applies it to practice. And I think I will stop here. I could talk quite long about his achievements, but what you are here for is his talk. And the title of his talk, as you can see, is AI-based convoying of leader-follower autonomous vehicles. And I'm looking forward to your presentation, Saeid.
Thank you very much. Good morning, ladies and gentlemen. It is a great honor to be here and in this beautiful place of Sarawak, and to be part of this IEEE SMC 2024. And I would like to thank the conference organizers and also the conference general chair inviting me to deliver a keynote speech. So the outline of my talk is going to be around robot-based motion simulators, and there's a reason that why I've selected this topic, you will see, and its relationship with autonomous systems, and then controller designed for autonomous platform, system design and build, and test and evaluation. And again, test and evaluation, in my opinion, is extremely important. And when we talk about test and evaluation, I want to show you that the kind of test and evaluation I've done, what it is, and how we have gone about it, and the level of complexity is involved in terms of real test and evaluation beyond laboratory. But before I do that, I actually work for Swinburne University of Technology. Allow me to show a few slides about our university. Our university was founded in 1908 and is among top 1% universities in the world. And some of the areas of research that we have professors and academics, they are very active. They are in the area of nanoscale and ultra-low power electronics, working with CERN, and Italian National Institute of Nuclear Physics, ANSTO, which is Australian Nuclear Science and Technology Organization, and Institute for Nuclear Science, Kyoto University. This particular topic in terms of design of embedded electronics and radiation-hardened electronics is very important. This is one of the areas we are working on. Another one is the area of microgravity experimentation. We have a whole team And we often, we are part of the program sending bits and pieces into space and seeing that how, for example, certain bacteria and things grow and so on. So this is more for high school and early undergraduate students. In terms of remote sensing, AI for space, astronomy, and remote sensing, our team working with Planet and SmartSat CRC and Ernst & Young and others, and Professor Kai leads that research. And we do offer engineering courses, anything from certificate to all the way to PhDs. So the reason being, we're a dual sector university, not only producing graduate engineers, we also produce technicians, and from technicians all the way to PhD graduates. Currently, we sit at number 36 in the world in the area of automation and control. Just one of the School of Science and Computing has over 5,000 coursework students. By the way, we have a campus here at Sarawak. Some of you, as you have driven past from the airport, you would have seen. We've been here for over 20 years in Sarawak as one of the campuses. So, and then some of the other research which is relevant to autonomy partially is data-driven road asset maintenance for smart cities. Here we have worked with the city council, put a number of sensors on a series of trucks, and these trucks, as they drive around the city, scan, collect information, and look at the road conditions, look at the road sign conditions, and various things, cleanness of the road, and so on. So and then feed that information back to central points to create a cleaner environment. But at the same time, if there are need for maintenance, every day we have up-to-date information about every single road around Melbourne, for example. Another area we talk about robots, large robots, robotics. So we have several of those at our university in Swinburne, but different use of those robots. So we are using big robots to 3D print concrete. So this is a very large work envelope, maybe 1/3 of this auditorium, and can print concrete. And you can create new design, complex design to be prototyped. Then in terms of laser cladding repair and aerospace defense component, we work with a number of defense companies with US, Australia, and around the world, and we have some project around JSF F-35 in terms of sustainment. So these are all the hard work of our research area. Another one is NanoLab 3D and nano micro printing. The guys, they are very active in that area of research there. And I think this is the second last, modeling, advanced modeling and simulation. We have several researchers. They are looking at design of better helmet, whether it is a bicycle helmet or combat helmet. And in fact, a new design of having a airbag inside the helmet. And then doing biomechanical analysis, modeling simulation, FIEEE, and so on. And finally, one team, they are working on certain types of corrosion resistance coating for anti-fouling. This has a huge application from defense, Navy, all the way to contact lens manufacturing. Because they have similarities, and we have a national center of excellence around that. But let me come back and talk about the topic here. I want to first specify and define a couple of terminologies, human in the loop and human on the loop. So a definition of human in the loop here, machine that performs a function for some period of time, then it stops and wait for human input before continuing. By the way, can this clock, can we start this clock? Control desk, hello? Can you start this clock, because it still sits on the 45 minutes? Thank you. And then human on the loop. That's machine that can perform a function entirely on their own, autonomously, but have a human in a supervisory role with the ability to intervene if the machine fails or malfunctions. So human in the loop, human on the loop, but have always argued that we never want human out of the loop. And I've put my neck on the line, and I've argued for many years, and that's my position. And there are some good reasons when you want to develop for the military and those kind of things. You don't want human to be out of the loop. You always want human to be at the apex of control decision making. This is my position. So in terms of precision and sensing in autonomous system, so precision involves sensation and interpretation, includes sensation for evaluation and detection of object in unpredicted environments. So this is very important that there are, if we can have some sort of prediction in an environment, if we are talking using vehicle other than cities, then the unpredictability plays a greater role. So in terms of then sensing, autonomous system requires enabling sensing technologies. This is for 3D measurement, state estimation, intelligent mapping, and object recognition. Not all of the objects that we do in the city area is the same as if you wanted to use for military use. So there are some differences. So then all of it comes down to trust. This notion of if human is in the loop, how can we gain trust between human and machine? If human is on the loop, how do you achieve that trust? And then how machine trusts human? Is there a need for that? And then finally, how a machine trusts another machine. So I'm talking about semi-autonomous and fully autonomous systems. If you go back in time, I think it was around 2000, when I was looking at robotics, I looked at backdrivable system, haptics, haptically enabled teleoperative system, and developed a series of technology. By the way, I keep saying I. So none of it is me, it's all the team. So if I use accidentally the word I, so put we and all of us, okay? We developed a whole series of technologies, and some of it were used for counter-ID task force, remotely deploying, using the system. So the robot, they're haptically enabled, so remotely we can defuse bombs and so on. But as a result of that journey, looking at all of the haptic device manufacturers, such as Sensible, Force Dimensions, Haptions, and so on, looked at the capability of those haptic devices, and the kind of capability we were after, which was multi-point haptic, did not exist in the world in a rugged manner to be field deployable ready. And that's where we went back to fundamentals, designed and built our own multi-point haptics devices, commercialized it turned into a product, and then went into utilization. Now, playing with haptics, backdrivable system, making teleoperative system haptically enabled. In parallel, I started looking at motion simulator. This was when Gino de Gaulle, he actually patented a robot called Robocoaster in Europe for theme park ride and so on. I approached him, I said, look, I'm in a university, I'm not into games, or because people, they won't take me seriously if I talk about theme park ride. But however, I'm interested to enable this technology to make it into a motion platform, and to put human in it, to make it backdrivable, to turn it into a flight simulator, and then to make it into land vehicle, land-based simulators, and so on. And the beauty of this system was that the reachability and work envelope was far larger than a traditional motion simulators that were in the market. So those are like golf platforms, Stewart platform. And then playing with haptic technology, looking at haptic steering wheel, haptic gear shift, haptic pedals, and all those kind of things that having had that background enabled to actually put some novelty into this platform, saying that how it is fundamentally different than traditional motion simulator, and in particular it is haptically enabled, and why you need a haptically enabled motion platform, because when you are if you use it for driving or flying simulator, to give that realistic feedback over and above motion sensation in terms of development of your washout filters is very important, because all come in and give you greater sense of motion and realization of it. Then start unpacking this technology, and the more we went in, the deeper we look, the more number of PhD students we put, the more money spent. So I'm talking now millions and millions. And then obviously being in the university, money doesn't come, so applied for equivalent of your NSF Science Foundation grant, and in our case was Australian Research Council. So I've received several of those first to design and develop platform, systems, and so on. I'll show you a few videos in a minute. So we had to design gondolas, look at vehicle dynamics model development. So these are some really serious areas which requires really deep knowledge and a lot of automotive or vehicle manufacturers, whether they are land vehicle, air vehicle, or marine vehicle, that they are really worked in this field because that's their core business. So we're entering in an area and we're blessed that since the idea was crazy enough, was novel, it attracted automotive car industry, some of the largest in the world. I won't name the car companies because I'm not advertising for any car companies, but you would have heard about those big giant companies both in US and Japan and so on. How we argued this system is better than traditional system was that the range of motion it gives you is far greater than your traditional Stewart platform. And then I identified the holy grail of where you need one particular range of motion that traditionally in automotive industry they never look for, okay? And it was a military application. In particular was driving tanks, and then when you are going, at the knife edge on the top of a hill, and then you have 55 tons vehicle, then where is position of your barrel, and then how you need to maneuver, how you need to actually control your throttle to drive, it becomes extremely important, extremely important. And there were no motion platform on this planet that could provide that. So we had General Dynamics, Lockheed Martin, Thales, and so on. They were and the CAE systems and so on. So they all have, for 40 years, they've been designing, building motion platform. But nobody had identified that capability gap in the market, I identified that and then won a contract with defense and provided platforms. Now, let me come back here to show you what this system does. Okay, I'm there. I'm trying to find my mouse to see if I can get, okay.
Give you a warning. If you're a high-tech junkie who gets jealous watching someone else enjoy the latest and greatest thrill ride, look away now. On the other hand, if you're about to jump into a military chopper or a fighter aircraft and go into battle, you've got to check out this. It's called the Universal Motion Simulator, or UMS. Where a pilot is perched on a 7-metre long robotic arm, capable of exerting up to 6 Gs of man at the controls of this next generation.
So maybe I'll go a little bit before, so we have a sound system.
It's called the Universal Motion Simulator, or UMS, where a pilot is perched on a 7-metre-long robotic arm, capable of exerting up to 6 Gs of force. That is impressive. The man at the controls of this next-generation motion simulator is Professor Saeid Nahavandi.
The reason I'm pretending that I can fly, but I can't fly a helicopter a little bit through the simulator I've learned. But what we're trying to show here, in terms of designing and building a Black Hawk helicopter, for example, the kind of range of motion it could give, the traditional simulator could not. And then a particular area called upset training, if any Air Force pilot here, they will know. So to provide upset training, you need to have range of motion which traditional Stewart platform cannot provide you. And all of a sudden, this became really a popular platform. So it was a theme park ride. I turned it into a simulator with a capability gap, and then I actually pushed to win projects and research. Now, then we looked at other types of vehicles, and then I didn't stop there. I developed a version that sits on a container base. Then you can take it anywhere. So you can put it on a ship, you can take it to any site. So we call this one a mobile UMS. And again, the devil is in the detail, large load, safety, you're putting human inside the machine. First time when I actually, I always put myself inside all of these machines, vehicles, and so on, and they video me. If I didn't die, that means it's good for other people. If I died, I will know what happened to me. So then putting it on system like that to make sure that it is safe, and to get all of the safety certification to go to be used in industry, I think that step is extremely important. So that's what I mean, that taking it from the lab, but once you actually want to turn it into a product or to be safe enough to be used, there are other level of complexity in terms of engineering. And then develop another version called this UMS 360. So now is a giant cooker robot. In fact, let me show you what I mean by that. Is this system. So you have an entire system rotate. So slip ring modified the whole controller system design on it, and direct drive linear electric motor, a good number of tonnage on it, and then in terms of control, then back drivability. So this particular system has 3 continuous axes of rotation. And then the only other one in the world is DLR in Germany. But this one has other capabilities that DLR doesn't have. So that led us to actually have a joint research project with DLR. Then going back that to validate the simulator, to give you that real sensation, then to become a platform for R&D, and then to put a crazy driver in it, then to run edge cases, dangerous cases, to collect data which then can be used for your AI and machine learning for your autonomous vehicle. That's the connection. A lot of Carla and other software out there, when they are trying to input edge cases, is very different when you are actually putting all of the vehicle dynamics behavior of a real vehicle. You have validated that the simulator is almost a true representative of a real vehicle, and then you drive safely, do crazy thing with it, so produce all of the data for edge cases for your autonomous vehicle to to learn. So this one, let me go again here. So here, look at top right is sensorized vehicle, somebody sitting in it, by ADAS system running, but it's connected to our motion simulator under here. The person sitting get exact motion sensation. So we had put IMU sensor on the seat here and on the vehicle. They replicate, produce almost one-to-one. So then by bringing people from proving ground working with us, and those are the ones that car industry use them when they are actually developing vehicle prototypes to validate our simulator. Then we were confident that actually the simulator now can produce almost realistic motion of a real vehicle. And then after that, then we said, okay, it's great. Then maybe the simulator can be used as a prototyping platform for car industry. Now, a lot of car companies, they have simulators that these days they use simulator as part of the prototyping to reduce the number of prototypes so they can reduce that product design cycle, reduce it, and also reduce the cost. And then do a lot of experimentation. Is cheaper in the simulator than doing in the proving ground, like nighttime driving, visibility, and ride, comfort, handling, and all the rest. So this is where we landed actually working with car industry. I was talking about that using that big simulator. Once we actually sold many of those, so that went, set up a company, startup, then defense bought it, and 80, 90 people employed as part of the company. Now we are competing with CAE and you know, Thales of the likes and so on. We secured that market. Then I went back, looked at that. That particular system can produce high amplitude but low frequency. So worked with a company in the UK, Ansible, redesigned their platform, and then created again another platform. This one won Queen of England Design Award 3 years back. And so has 8 degrees of freedom. And this particular system, you can draw. Okay, no, you cannot. I'm on a different window, you cannot see. Maybe what I'll do, I'll show you one of our very excited driver, you could say that. So we have a proving, we have a racetrack, and then this one, you can see is 360 degrees wrap around. So all of the scenes, they look realistic. This is Bathurst. And then you can drive at high speed, 250 miles an hour, you know. And then you see that how the vehicle behave, should it behave in a particular way, and then what happens to you. So we put a series of sensors on the human, and mental load, galvanic sensors and things. And then really when you're sitting on that simulator, being ordered to go on complete time is really stressful. So we could use this to collect information at the same time to look at human behavior, human-machine interaction, and so on to the fullest. So then I use the platform in terms of behavior analysis, how people take orders, whether they take order under stress. Then there were other things in terms of taking drugs or alcohol influence. So there is a whole heaps of research you can do safely on a platform that can really give you the kind of motion fidelity that is needed. And the other thing was people to sit in it for hours to drive to see what happens. So instead of really driving long distances, then you put people inside the actual simulator. So then collected lots of data as a result of this. And then top right, then there were two platforms, land, small vehicle, and then say 40, 50-ton vehicles. I myself, I can drive big rig, you know, articulated, non-articulated. I'm not a bad driver, by the way. I've driven for several years for test and evaluation. So then the idea was that to create an environment and simulator for the big rigs, not only driving forward, as you can see, the inclination is quite high, you know. These are, again, in the proving ground. When you have a big rigs, you're going down and then reversing. Nobody in the right mind reverse on a really sloped area. That is not part of the test. So I was creating an environment, simulator, a simulation environment, that when a big 50-ton vehicle has gone down, then you stop halfway, and then can you reverse backwards, and then there is a roundabout. Going forward in the roundabout with the articulated lorry is easy, but reversing back around the roundabout, reversing and roundabout is the next level of complexity. So then that particular system, we actually used it for collection of data, also for training driver. But that time, then I had our military having had enough confidence that we do understand big vehicles, big rig, we can drive big rig. We have designed and developed a whole series of, in mid-90s, late 90s, Formula SAE. So we understand engine management system, we understand how to design and build a smaller platform. And then the concept of bigger platform, obviously diesel engine with double gearbox, automatic and so on, very different. So they gave me the chance to actually lead a major project to design and develop a whole convoying system for big rigs. And this project started. So then looking at levels of autonomy, so I apologize if you already know. So we're looking somewhere, first this is a definition, I won't read it, so you know that we're, what level we are talking about, level 2, level 3, and between level 3 and level 4. So the technology I developed, it is around level 4, the autonomous convoying sits between 3 and 4, okay? So there were a lot of challenges, and at the end I will tell you what are the challenges, but I had to deliver the project. So we looked at the autonomy subsystem. So I'm aware that Waymo, you know, all of the other vehicle, autonomous vehicle and so on. The problem here is that you bring your best vehicle, Tesla and so on, we take it in a contested environment, meaning in a bushland, riverbed and those kind of things. All of those vehicles fail. The reason, if there is, military just kidding. Lockheed Martin in the US have, and I know exactly where their technology was, and then we were building beyond what Lockheed has done in terms of their autonomy. So looking at coming up with autonomy subsystem architecture, so follower vehicle, lead vehicle, and then I was lucky enough, I got my training with defense, could drive big rigs, and was trained to actually train other people to drive big rigs. Not only that, then I became the loader, loadmaster loader. Loader is the next level, that you load these vehicles on a transporters. Now, when you want to load this vehicle on a transporter, you have only ½ centimeter of error when you are taking on. Otherwise, the vehicle falls off and good luck, you kill yourself. So they forced me to do that. So I actually understand the length of the vehicle, the level of fidelity, level of control, that if you make a mistake, you pay a big price. So I became good at it as it happened. I have videos I can show, and then I had to train others. So I trained researchers to be drivers, to be engineers, from the laboratory to the field. So now we are talking big robots. We are not talking small robots, you know. Traditionally, the way it's done, people on the proving ground, not all of them, they are good engineers, and they are good AI machine learning developers, they are not control engineers and so on. But bringing the guys that actually sitting in the vehicle, feeling it, and coming back to the lab to develop the technology, it takes next level of acceleration towards development of the final system to shortcut that. That's what I try to achieve. So in terms of perception, obviously all of these object detection, lane detection, road segmentation, and then you have localization, local, global, obstacle avoidance, and then you have to, being a land vehicle, you have to do steering and acceleration and brake. Now, I just want to ask, how many people do we have here that they can drive really big rig, big truck with a diesel engine and 30-odd gear combinations? We have only one in this crowd, okay. Oh, fantastic, I didn't know. So we are good truckies friends now. Okay, that's great. So at least we have two people here. When we talk about big rig, you know, if it was traditionally double the class, you are going up the gear and then you are going down the gear and you have to study the road, know the inclination, know what gear you want, how to rev up. So there is an art in driving when you're driving manually. It's not like accelerated brake, accelerated brake. Why am I mentioning that? Because the control system you develop is very different. Like your traditional electric motors, you know, brake acceleration. Here, larger, much larger mass and momentum, and then the turning point, the distances between front wheel, steering wheel, whether it is two-wheel steering, four-wheel steering, you know, all-wheel steering, and then the way it works in terms of locking your diff to get the traction you need on different terrains is not all like your highway with tarmac and so on. So we are talking something totally different. So all of these problems we had to look at to solve. And then in terms of obviously being a big rig, if something goes wrong, something really goes wrong. It's really dangerous. And then so I had to make sure as a project leader to make sure we never ever have any accidents. You know, sometime in the lab, a robot crashes something, you say, never mind. A software fails, you say, never mind. Here, you cannot afford anything to fail. You know, otherwise it will be catastrophic. So that brought back to give defense the confidence that to put 3 levels of safety. So we have high level AI, and then we had middle level control, and then low level control, and then how we actually achieved it. Then, being a guy, being educated in 80s, went back to my roots, to said everything I have to record it, to develop flowchart, to make sure that, to show that everyone, our client, understands step by step, to do code design, code development, bring subject matter expert, what we are doing, is it right or not? Do they accept it before we, in fact, even start doing first line of code? So that was the approach. It gave them the confidence that what we are doing, it was the way they wanted. So when I say that we develop controllers, it's not that cardboard boxes. As you can see, that they are ruggedized controller. We developed secure mobile cloud sitting on the back of the vehicle with all of the control system, GPUs and so on, with all of the climate control. And all, you can see that they are all military grade connectors and so on. So pushing the team to that level of, design, development, ruggedness, I think is a little bit different again from the labs, operating in the labs. So again, everything had to be retrofitted, meaning that within 2 hours, we take all of the autonomy pack off, and then it took 3-4 hours to put the autonomy pack on. So then it can be any vehicle. Doesn't matter what is the vehicle, make, model, and so on. So in this case, we had all of these German vehicle MAN. By the way, German military, themselves were interested at how we have done it in Australia. So this is autonomy workflow, so LiDAR, cameras, GPS, radar, and so on. And then in terms of localization, what we did in terms of motion planning, and then motion control. So in terms of connectivity, so you've got up, that means I have 5 minutes. Okay, so I'm gonna move a bit faster. I won't run some of these things. So these are the LiDAR we used, and then we looked at in terms of pre-processing, ground filtering, object detection, shape detection, using all of the techniques that everyone knows here. I won't bore you. Perception with LiDAR, perception with object detection with LiDAR. And these are all we had to actually do locally for ourselves, for the vehicle, in a secure, safe environment. Nothing goes to the cloud. We have our own mobile secure cloud, and so on. So then start putting some of the algorithm, taking the vehicle on the road, start trialing it in terms of localization we looked at. In terms of motion planning, we used different algorithms to see what works, and then all of these algorithms, I'm sure many people in the crowd, they've been playing with MPC and combination and so on. So we actually played with all of that, and then always used in the simulation to see what simulation does before we start putting it on a vehicle. And then when it was on the vehicle, I was the guinea pig actually to experiment on the vehicle before taking it on an actual convoy. Then collecting all this data, all of it was collected. So this is over 3-4 years, hundreds of hours of data we collected to actually fully analyze and then show our client. And then from an AI perspective, we looked at again, you're aware of all of that. Perception 1, we looked at, from 2007, DARPA Challenge 1, all the way to, multi-input, multi-output, end-to-end. And we looked at perception 1, and then 3D detection with camera, LiDAR detection, panoptics segmentation, depth estimation, LiDAR segmentation. So all of these kind of technology we went, and then we identified issues with it. So these are, I'm talking up to 2023. So when you go back in time, technology, everybody was developing, and in parallel, we were looking and developing algorithm with them moving forward. And then, so perception 1.5, looking LiDAR, radar, and then aggregation fusion. And then we looked at issues with perception 1.5, then perception 2, and then multimodal. And then really, then that was where we started looking at fusing the sensors, both object detection, lane detection, road segmentation, and so on, and then start producing something. And so now this is, look at it, and going extreme. Pulling handbrake on a big truck. Watch what happens. And this is me driving it. Everyone thought I'm crazy. This is at 60K, then I went 80K, then 100K. And then I learned that at what speed you go before just you kill yourself. And I didn't kill myself. And the way I actually burned the tire, I think if you've driven big vehicle, 50 tons, like big tanks and so on, braking, the whole ground goes on fire, with the friction and so on. So I was trying to go to look at some of those extreme conditions. So here, for example, the truck convoy is going and the person jump in. So I had got the airbase to myself, then using the airbase grounds to actually do a whole series of experimentation to see what it is. So when these vehicles, they're following, the vehicle follows what that lead vehicle at the time was doing, but then it has its own local autonomy, local planning, local control. So it's 2 levels to it. And then, so prove that we jump in front of this vehicle and it stops, doesn't kill anyone if we wanted to. So let me move because there are many things. So here going totally, and in all of these things we had to bring camera crews to prove that filming UAVs in the ground, that it is really autonomous, nobody pulling wool over anybody's eyes because the money was involved in terms of delivery. So when we talk about delivery, these are, you know, test and evaluation at this level, that really it gets recorded, auditor comes, you know, 30, 40 people sit, evaluate, record, and analyze, and go through depth of everything you're doing. And then filming and producing as evidence. So then, in one of the things, we had the chief of army, we were indoor, they said, we want this thing to go inside the exhibition hall, large exhibition hall, prove that it autonomously can work in a GPS-denied environment. So we had to prove that. Again, we have videos and put chief of army sitting in it and driving fully autonomously. And then here, this is one of the earlier trials that we have a dead man's switch, that legally you have to have that if you are in areas that to prove that that there is somebody if something goes wrong. But the area you see, no lane marking, it's the area bushland. I won't say where it is, but there are things that your normal off-the-shelf vehicle technologies that Google X and other people developing, Apple and so on, it cannot perform in these kind of environment. That was the capability gap. And then with it is single, convoy, and then came up with the environment that you can define in a convoy how many vehicles to be, which one to be lead vehicle, and then if lead vehicle taken off, killed, then other vehicle automatically become lead vehicle, and then you decide which one to become lead vehicle and so on, and then how to do collision avoidance. So some of these work that I'm talking about, BAE system, originally they were doing, and then the contract I got beyond BAE system was that we did obstacle avoidance that BAE system could not deliver to our defense. So here you see so these are highway driving, by the way. We put these autonomous vehicle on the highway while there are other vehicles there on the highway. This was the first time in the world we achieved that. Going inside the riverbed and so on, you see that actually the vehicle goes, you see, so we proved that if there are water, flooded area and so on, some of these, it goes up to 1.5 meters in the water, you know, and then comes out. And the software, the sensory system works, it still works. That's very important. It's not only having the system, whether it's the sensory system work, and then how much of redundancy you have put between the sensor. If you don't have LiDAR, can you use visual tracking? If visual tracking doesn't work, combination of LiDAR and radar and so on. And if your comms fails, we had 3, 4 different ways to enable it, all the way satellite communication would kick in, that you always have comms. So, and then we have dust, rainy, you know, puddles on the road and those kind of things. When there is a big hole and big truck goes, then in terms of you control the vehicle, then now human is not controlling, the controller has to control it, that in terms of its stability control and so on. And here it is, I will finish in a couple of minutes. Going in the highway, and so as you can see, other vehicle passing, and then if there are some other vehicle cut in, what do you do? So that was when we were first trialing, that was one of the biggest worry, that if he jumps, if it is autonomy, not to mention that the person sitting in, your feet is up in the air, arms in the air. I don't know if you have ever driven in a car, feet up, hands up, to be ready to jump in. So I did a lot of experimentation on myself, that what is that optimum time a human with the right mental state can jump in to take over an autonomous vehicle? What is that number of seconds? Because you lose your spatial orientation, you become disoriented if you were reading something and suddenly look up, and if is that the time that you need to take over, it's quite critical. What is that time, you know? And it varies from people to people. Anyway, so in summary, we tried to develop an end-to-end perception for autonomous vehicle. So this was everything from concept, controllers, putting in the vehicle, creating secure cloud, then demonstrating it, making sure it works and it is safe to use. So it's a long journey it was. Not to mention how do you put the team of postdocs, suddenly they are truck drivers, suddenly they are working, putting different hats. The project, all of the credit should go to several people within defense. I had the pleasure of working with them. And in the journey, as an academic, I was lucky enough to write some papers with others. And then when it was mentioned that there were some organization lucky, and I was lucky enough that some organization to give me some awards in Australia. With that, I stopped there. Thank you.
Thanks a lot, Saeid, for this very inspiring presentation, and I think you could feel his dedication to his work. Are there questions?
Good morning. Frank Flemish from Aachen University and Fraunhofer. Thank you, Saeid, for this really interesting presentation. I'm your German counterpart. We are supporting the German DoD in leader follower trucks and supporting Rheinmetall. By the way, we are driving the same trucks, and I'm also a truck driver. So, having said that, I'm really impressed by what you did there, and you showed mainly the technical stuff. You mentioned that there is the necessity for the driver to take over in certain, we call these edge cases. I wonder about what kind of human-machine interface you developed. I mean, we are here at SMC, so it's about systems, yes, the technical part, but it's also about human, that have to take over these vehicles. They have to be on the loop. You mentioned takeover times. That's an issue also of the human-machine interface. So how did you manage the human-machine part and the ergonomics in this project?
For sure. So this very complex question, multidimensional. The ergonomics said, how do you create a retrofittable technology on a platform that you can both machine drive by itself, but ergonomically to be designed that human can jump in to take over. That itself is a topic. Yeah. Yeah. We spend a lot of time to look at the position and so on, yeah. and because otherwise it is a runaway truck, 20 ton, 30 ton. How are you going to stop if this thing goes? It's not like a car that you can put something, a bulldozer or something, slow it down. So we looked at that. In my lab, we had a whole series of looking at human modeling perspective. We had created avatar, and then also from humanitics, with both dummies, highly sensorized dummies with lots of sensors on it. So to minimize risk in terms of step-by-step testing and evaluation. Now, we used several papers in terms of EEG, FNIRS, galvanic sensor, eye tracking. So that was, I had a whole lab of maybe 20 researchers working from that dimension. Now, using them, sensorizing us, putting in the simulator, understanding what we need to do, and then by sensorizing ourselves on the vehicle, and I also have other people sensorized sitting as a passenger, not telling them what the vehicle is going to do. Because there is another aspect. If you have a personal carrier, no driver, how do those guys behave? Do they panic? What do they do? The level of discomfort, stress level, and so on. So we looked at that perspective as well. Now, then when it comes in terms of command and control, we must have spent maybe 8-9 months in terms of human-machine interface, symbology, what to be there. And all I can say that a lot of motivation came from younger kids using mobile phone, without any manual, without reading anything. They just wanted to see and get the information. Only a single page talk to you, give a lot of information, but right information at the right place in terms of, I mean, I haven't talked about battery management, that huge, you know, several kilowatts of power. We had GPUs on board, you know, doing real time. None of it was on the cloud. It is all on the field being doing, you know. So there were all that aspect of how do you design machine interface, human-machine interface. Unfortunately, a lot of it became published because it's military. But my knowledge and understanding I'm using in other projects, you know, how to go about and how to develop and how to progress autonomy. I was visiting Google X 2 weeks ago in San Francisco and so on. So looking at what they have, but it's still a long way have to go. I was in San Francisco. I personally confused some autonomous vehicles because pushing them over the edge case, and then poor vehicle had to be there for a while. Right. Yeah. So these edge cases is very important. How to create edge cases, and then in a safe environment, and then get your model to be trained on those edge cases. If you ask me one thing, so all of that project, all I can say that it was a huge learning. Now I have learned how little I know about autonomy. That's all I can say. I'm not claiming that we actually achieve autonomy. It posed a lot of questions, a lot of unknowns that we now need to focus on and work on. Edge cases, I think, is one of the most important area, but not the way edge cases normal people look at that. Some of the software, people provide software on the edge case simulation, they're no good. They're really, because behavior of this big vehicle is very different. And you see car turns and, you know, traffic lights goes, you know, you don't want to brake, it stops. It's a vehicle like that, it doesn't brake. If it is downhill, uphill, you know, all of the terrain plays a major role. And so all of those kind of things, out of necessity, I had to actually provide solution. So from a human-machine interface, then step by step, we sensorized, we looked at what works, what doesn't. We use subject matter expert, and we use end user. So a lot of soldiers that were involved. So that's, as I said, it was a code design, code development. It wasn't that, oh, we know engineer, we are expert, we develop something, you use it. No, it wasn't like that. We got them involved. We got them early on to use with us. So we fast-track this innovation cycle.
Okay, thank you for clarifying this.
Thank you.
And maybe in the break we talk about minimum risk maneuvers.
Yes, yeah, for sure.
Thank you.
Thanks, Frank. Are there more questions? Maybe one short? Yeah, please come to the microphone.
I'm Shanghai Yang from the University of Reading in the UK. I have been working with BAE systems for a couple of years before in the UK. I just wonder if there's a number of autonomous vehicles working together for a real military task. Probably you need to using wireless communications to build established collaborations among different vehicles, or even have a central control to the team. If that is the case, do we need to consider the security risk? Say, if somebody hijack your systems through the wireless communications, and how do you have any protection for this kind of the risk? Thank you.
So, unfortunately, I can't answer this question, okay? And the reason is, yes, we have looked at it. Being sensitive, I can't. All I can say that people will not have access to our system. That's all I'm going to say. And the kind of communication system we have talked about, you mentioned, we were not using. So it's not the traditional communication system. So there were many layers of redundancy. It's not the communication system normal people have access to. And then there are various satellite and other things. And there were redundancies. All I can tell you that we intentionally, constantly failing certain system to see that each vehicle can become autonomous by itself. You know, I said that there is a global autonomy and local autonomy. So each vehicle can become suddenly a leader. That was very important. So you could feel the communication between all of the vehicles, still they work. Because they knew that what was the overall objectives. Like me saying, go from here to Kuala Lumpur. So you know that that's the role, and then you're following. But it doesn't matter if your other vehicle fail in a convoy, but still you know. And if you know how to do local planning, you know global planning, you know local optimization, you know global, you know how to get there in real time. So everything was dynamic. And there was a lot of redundancy in terms of mode of communication, in terms of failure, in terms of even GPUs, you know, they were working, there were redundancies, you know. And some of it I learned from aircraft manufacturer. You have quadruple redundancy, triple redundancy, quadruple redundancy, because you cannot afford that one controller only going to give decisions. So you have 2, 3, and constantly they are comparing, and then you get the end result. So if one fails, still 2, 3 of them, they are there, they are working. So it was a more expensive system, and then that has a pros and cons. Since you're using now GPU and those kind of things, they're power hungry. Power hungry, battery. So there are other elements comes in. And then battery, then you have other types of energy generation system. We had to actually have it in the convoy. But it's all local. And assuming at any one time, any of these vehicles can be taken out by whatever means. And still they can. And I have a lot of videos demonstrating that. So then you look at the notion of cyber hardening. So we have a whole team working on the area of cyber hardening as well. But I'm sorry if I cannot give you detail. On purpose, I cannot give you the details, so I apologize.
Okay, thanks, Saeid.
Thanks.
Since we are already over time and the coffee break has already started, I would like, if you have questions, approach Saeid. He will be around today, probably also part of tomorrow, and he's available for questions. Thanks a lot for your attention. Thanks to Saeid again.
Thank you. Thank you very much.